Kia ora, year 12 and 13. Here's part 1, D and E of the 2014 paper. So one of these questions is yet another de Moivre's theorem question. That's the merit one. And then there's a very straightforward locus problem for the excellence question. I'm also going to go through and reteach a bit of locus stuff after I've done the question. So you might want to skip that if you're already confident with that. Okay, so the first one is an equation solving one. So the equation we're going to solve is this one. Z to the power of 4 is equal to negative 4k squared I. Right, so as soon as you see these questions, a couple of things should pop into your brain. The first is that we're looking for 4 solutions because it's Z to the power of 4. And the second thing is that we want to be working with polar form, not rectangular, because we're going to use de Moivre's theorem to find the roots very, very easily. So let's take a look at negative 4k squared I. Where is that? Well, it's down here. Here it is. So if it's negative something I, we can see that the argument is going to be 3 pi on 2, or 270 degrees, and the length of this is going to be just positive 4k squared. So we can start by rewriting z as r cis theta to the power of 4, and then fixing this up to have it in polar form, we're going to get 4k squared cis 3 pi on 2. So after that we get r to the power of 4 times cis 4 theta equals this. Right, how do we know that? Well, we can do this because of de Moivre's theorem. So write something like that down to show you reasoning. Okay, next thing we do is just the usual. We equate the, sorry, I'm losing my words today. We equate the moduli, and then we equate these. We remember that we're looking for 4 solutions. Okay, so step 1, r to the power of 4 is equal to 4k squared. So that gives us r is equal to the square root of 2 times k to the half, which is just root 2k. Now, hopefully some of you are looking at that and go, oh, she's made a mistake. She's left out the plus or minus. So I want to talk about why it's okay to leave the plus or minus out here. And that's because in this context, the modulus has got to be a positive number. So it's fine to just ignore the negative square root. In fact, it's correct to ignore the negative square root. So we just get r is equal to root 2k. So the next part of the problem is that we've got 4 theta is equal to 3 pi on 2. So that was this. So 4 times theta was this. So what will theta be? Well, just before we hop to that, we've got 4 theta equals 3 pi on 2. But of course we could have that plus another spin around, or another spin around, or another spin around, and so on. So just like with general solutions, this is not 3 pi on 2, it's 2n pi added onto the end. And that's how we generate our 4 solutions instead of just our first one. So theta is equal to 3 pi on 8 plus 2n pi divided by 4. Now I'm going to do something that you won't have seen me do much before, and that is not to simplify that fraction. In fact, I'm going to change that to make it divided by 8, and that's to help our brains instead of jumping to the calculator. So this is going to give me the 4 solutions. Right, so theta will equal 3 pi on 8. The next one will be 7 pi on 8. The next one will be 11 pi on 8. And the next one will be 15 pi on 8. It's also totally fine to write this one, 11 pi on 8, as negative 5 pi on 8. And this one we can write as negative pi on 8. And you'll see both of those done. I usually use the positive values, but I think this is probably more common. Anyway, here are my 4 solutions. The first one is going to be root 2k cis 3 pi on 8. The second one, root 2k cis 7 pi on 8. Next one, root 2k cis 11 pi on 8. And the last one, z cubed root 2k cis 15 pi on 8. Now, just if you are doing this in a screaming hurry in the exam, be really careful that you don't find these and just stop there. Because even though you've found the moduli, you found the modulus and you found the arguments, you have to write the complex numbers out because you're trying to write out the solutions to that equation. So it's not just an angle, it is the whole complex number. But here you're just asked to give it in polar form, so you don't have to do any converting back to rectangular. Alright, I'm going to go on to the locus question now. Right, so find the equation of the locus described by this. So I've got z minus 1 plus 2i equals z plus 1. I'm going to do it first and then I'll talk about what it means geometrically. So I'm going to start by writing z as x plus iy minus 1 plus 2i. So we're looking for the set of x's and y's that are going to make this relationship true. So the way to do this is just to reorder them so that we've got the real part first, x minus 1 plus I times y plus 2, and then this side we've got x plus 1 plus iy. Now we apply our definition of modulus, which is this. So this looks terrible, but as you know, because you will have done some locus practice probably by the time you're watching this, these are super easy from here. They really are the easiest excellence question you're going to find in level 3 calculus, I reckon, in any of the 3 papers. I can square both sides. You don't have the magic eraser in the exam, but I do now. So there we go. I just have to expand out. I get x squared minus 2x plus 1 plus y squared plus 4y plus 4 equals, it's not going to fit, x squared plus 2x plus 1 plus y squared. Right, we can clean up quite a bit of this straight away. Subtract the y squareds from both sides, subtract the x squareds, and I'm going to do the rest on a new slide. So I get 4y minus 2x plus 5 equals 2x plus 1. So it's going to be some kind of line, so I might as well write it in y equals mx plus c form. So 4y is equal to 4x minus 4, y is equal to x minus 1. So that is the locus of points that will satisfy the condition we started out with. So here's that line. So this is the real axis and this is the imaginary. Y equals x minus 1. So it just looks like this. In other words, the set of points on that big thick line is going to make this be true. So let's rewrite our condition and have a look at it. So z minus 1 minus 2i. On this side we've got z minus negative 1 plus 0i. So I think looking at it like that makes it a bit more obvious what we're doing. We're saying show me the points, z, where the distance between the point and this complex number is the same as the distance between the point and this complex number. So let's now draw those points in. Well, where is negative 1 plus 0i? Well, it's here. And where is 1 minus 2i? 1, 2 is down here. So just from looking, you can see that joining through there, that's the midpoint. So I know that must be part of the solution. Moving further along, you can see that all of those points on that line are equidistant between those two. Alright, so if you need to explain what you're doing, that's what the locus is really about. You're looking for the set of points that satisfy that condition. So it's nice if you can come back and rewrite like this, because you'll have a much better understanding. You're not usually asked to do it in the exam. What you might be asked to do though is to say, what is that locus? And so it's a line in this case. Okay, hope that made sense. Let me know in class if you've got any more questions on loci problems. Thanks for watching.